Yeah. So, Professor Dasgupta, you are here?
Yeah, I'm here.
Okay. So, I request Devolina to please start.
Good afternoon, everybody. I, Ms. Debolina Paul, on behalf of the Department of Physics, Assam University, Silchar, welcome you all to this international webinar on applications of group theory in physics 2020. This is a part of the Silver Jubilee celebration of our department. To mention here that the inaugural session for the event has been scheduled at 7:30 p.m. IST, depending on the availability of the keynote speaker. Now, may I request Professor Athri Deshmukhia, convener of this webinar, to say a few words about this event. Ma'am,
Thank you,
please.
Devolina. Sorry. Thank you, Devolina. And welcome. A very good afternoon to you all, whoever is present here. On behalf of the organizing committee of this 10-day workshop, this is a virtual workshop, of course, that on applications of group theory in physics, in different branches of physics, better to say. And I'm very happy that we are at the point of starting. It was a long exercise by the time we tried arranging the program, and due to the time zone difference, our keynote speaker is not available at this point of time. So he will be available only in the evening. So we have scheduled our formal inauguration at 7:30 p.m. today, and you must have received the invitation. But by this time, we are going to start our business. And actually, group theory is a topic, such a topic of mathematical physics that has extensive application in the field of physics. But to appreciate those applications, first of all, we have to recapitulate whatever we knew or we learned about the group theory in different course parts. So I am very happy that, and thank you to Professor Ananda Dasgupta from IISER Kolkata, that he has taken that pain to help us recapitulate everything, the basics, in a long 5 lecture series. And it is very kind of him actually that he has taken up this load. It's quite a load. And I'm really thankful that he has accepted this offer. And Professor Dasgupta is here. I don't want to waste any time for the students. And I would like to hand over the session to back to Devolina. She will introduce Professor Dasgupta, and then we'll hear a few introductory words from Professor Dasgupta, and then we start our real business. And I hope you will really enjoy this workshop. And this is a hardcore business, so please be careful. And I wish that you will learn as much as possible from this exercise. And we have all the eminent speakers here. Professor Dasgupta is an excellent teacher. You will come to know now from his classes only. And later we have our other stalwarts also in the whole thing platform. I wish you will learn many things from here. And don't worry about the attendance thing. We will see to it. This is not the only thing that your attendance. Try to learn the physics, and then we will see to the attendance. Okay. So thank you so much. I'm just it's over to Devolina.
Thank you, ma'am, for your kind words. Okay, so now towards the technical session, and as said by ma'am, the first talk will be presented by Professor Ananda Dasgupta. So for this, I request all the participants to please mute your audio and video during the lecture. Now, let me introduce Professor Dasgupta for you all. So Professor Ananda Dasgupta is currently the head of the Department of Physical Sciences, Indian Institute of Science, Education and Research, IISER, Kolkata. He did his PhD from Saha Institute of Nuclear Physics in 2001. He used to work mainly on Lie algebraic techniques in quantum optics, and now he is working primarily in statistical mechanics, general relativity, especially in the applications of the Roy-Choudhury equation. He started his teaching career from St. Xavier's College, Kolkata. Then he also taught in Jadavpur University, and he is connected with IISER Kolkata since its inception. and have formally been a faculty there since 2007. In the past, he has also served as the Dean of Academics in this institute. Apart from this, he has a number of publications in highly reputed journals like Physical Review, European Journal of Physics, etc. So, sir, please, and now I hand over this to session to start.
So can I start now?
Yes, sir.
Sorry, I couldn't hear you. Okay, thanks. Well, I must thank the organizers for inviting me to be a part of this wonderful program. In fact, group theory and its applications in physics is actually a very dear topic as far as I am concerned personally. Both for my, my work, early work was in group theory in a way, but even more than that, it's a really important part of physics and it's very nice to learn about it. It's important for various reasons, as you will see during the course of this workshop. But anyway, the introduction put a bit of pressure on me in the sense that a lot was promised about what I'm going to tell the audience in this particular 5 lectures that I'm going to give. Well, at the very outset, let me just say one thing. I am afraid that that I have actually sort of bitten off a bit more than I can chew here, in the sense that the entire topics that I want to cover in this particular 5 lectures is something which I usually cover in a course in, say, around 15 or 20. So, of course, what I'm going to do is I'm going to cut short many of the proofs. I'm going to sort of leave some details out. Hopefully, it will still be reasonably meaningful. And so if at any point of time, it seems that I'm actually going too fast or I'm just ignoring too many things, too many details, please stop me and ask. Although I understand that given the constraints of an online situation, you have all been asked to keep yourself muted. So it may be difficult for you to ask directly. If you write in the chat, I'm going to take a look at this from time to time and try to answer. The one problem is, of course, when I'm presenting, I cannot see your chat, so I cannot really directly, immediately answer any questions. But I will try to look back and answer whatever questions, at least whatever questions I can answer without slowing down appreciably. Okay, and on top of that, let me also say that despite the fact that this is a workshop on applications of group theory in physics, I have deliberately kept physics out of what I'm going to talk about. Well, not really. I'm going to essentially talk about those parts of group theory which will be useful in physics. So I have, for example, this is for any mathematically inclined person in the audience. I will not talk about, for example, Sylow's theorems, which are very, very important parts of group theory in the abstract, but don't really find that much use in physical applications. So my choice of topics in group theory will be guided by essentially what will be required for physical applications. And although I will not really talk about physical applications directly in my lecture, simply because there are other people, other eminent speakers who will talk about those things, I will try to indicate places where physics will come in during the lectures. So let me just start by presenting. Let me present my slides here. Let's see. Okay, I hope. Okay, let's just check one thing out. I hope you can all see the slides, right? Now somebody will have to speak up and tell me because I can't.
Yes, sir, we can see it.
Thank you. Thank you. Okay. So as you see, my heading is group theory, the bare minimum for physical applications. I will try to. Group theory is a huge, huge topic. I will try to keep things as short as possible. In the process, I will actually omit some topics which many people might consider to be very important. But I have to, because simply A, because I don't know everything about group theory. Nobody today does, I guess. But more importantly, because there are many topics which will be left out simply because of want of time. So let me now start with the very first topic, which is symmetry, in the sense that, as you all perhaps are already aware, the major application of group theory, by no means the only application, but the major application of group theory in physics is because physics has a well, intimate connection with symmetry, and the symmetry principle and its applications constrain physics in a very big way. So let us start with a very simple example of symmetry, a symmetry of a physical object, in particular, the symmetry of an equilateral triangle. So what I have on the slide now is a picture of an equilateral triangle with the three vertices A, B, C labeled, but please note that the three vertices are completely identical, and the labeling is just a way for us to keep track of what's happening. The labeling is not an implicit feature of the triangle. The three vertices do not come with extra, with different labels and different corners. Okay, so what can you do to the triangle? Sorry, is there somebody trying to say something? Is there a question? No. Okay. So now we are starting with this triangle, the ABC. The three vertices that I said have been labeled, but that's just for our convenience, just to keep track of what's happening. The question is, what can we do to this particular triangle without changing it? In other words, if I asked you to close your eyes and did something, and you then opened your eyes, you would not be able to tell the difference between, or tell whether I've done anything or not. Of course, one of the things that I can simply do is do nothing. And that's always a symmetry operation. Doing nothing, also called the identity, it's universally denoted by the letter E. Well, much of group theory came from Germany historically, and E, of course, is ein, the first letter of one, or unity in German. So doing nothing, the identity operation is always a symmetry. And on the top corner here, what I've also done is I've tried to denote another way of looking at the symmetry operation, which is just telling you what happens to the vertices. The vertices ABC of the triangle, this is the top row, this is where they were before I did the operation. The bottom row says where these vertices land up after the operation. Of course, if I'm doing nothing, ABC stays ABC. That's it. Okay, so that's doing nothing. What else can I do? I can just pick a median, which is passing through the vertex capital A, and I can actually reflect in that median, right? So if I do that, what will happen is the vertex A stays where it is, the vertices B and C switch over, and as you can see in this notation, you can see ABC has become ACB. That is, A goes to A, B goes to C, C goes to B. Most of you may already be aware of this notation. This is the notation for permutations. You are permuting the three vertices A, B, C by doing a symmetry operation, and this notation simply tells you where each one of the elements end up. Okay, so that's a reflection. That's reflection in the median A. Then another operation can, of course, be a reflection in another median, the median going through B. And that will keep the vertex B the same, switch A and C, and you will end up with ABC. A will become C, C will become A, and B stays B. Similarly, one more reflection is there, which is, of course, the reflection in a median through the vertex C, which I'm denoting by the small letter C here. And that is going to interchange A and B. These are not the only possible operations. There are other operations. For example, if I were to rotate the triangle by any arbitrary angle, it's not going to be a symmetry. If you saw the triangle before and after the rotation, you would definitely know that I have rotated the thing, right? You can see the rotated version is different from the original version. But if I rotate it by just the right angle, which in this case is 2 pi by 3 or 120 degrees, I again get a triangle which is exactly identical apart from the labeling of the vertices, and that's a symmetry operation which I'm denoting by the letter D. So this rotation by 2 pi by 3, I'm just going to call it D. All these operations have special fancy names, especially say when you're using group theory, say in crystallography. For example, this thing, this rotation by 2 pi by 3 is called C3 because it's a threefold rotation. These reflections are basically sigma V1, sigma V2, sigma V3, and so on. But that nomenclature is not going to be of interest to us right now. We are just going to call them simply E, A, B, C, D. D is this one, where, of course, all the vertices move. A goes to B, B goes to C, C goes to A. And finally, I have one more symmetry operation, which is if I rotate by 2 pi by 3 twice, that is, rotate by 4 pi by 3, I end up with a rotation which I'm denoting by F. That's also something which leaves the triangle the same before and after. Now here I'm assuming that we are making life simpler for ourselves by sticking to only 2 dimensions. So things like flipping the triangle over, say picking this median once again and rotating by 180 degree about it, is something I'm not going to consider right now as a separate operation. So that way I get 6 operations, and these symmetry operations on the equilateral triangle, each of which leave it invariant, can be denoted either in terms of these reflections and rotations or by these permutations on this side. And okay, the 3 permutations in blue are reflections. The 3 rotations are in red. Okay. Could you just excuse me a moment? I have an official call coming in. I will just be a moment. Sorry about that. The trouble of working from home is you have to also keep on attending other calls and stuff like that. Okay, so let's just continue and complete this part. This is, of course, pretty familiar to most people, I guess. But the important point is this is one set of 6 symmetry operations which will recur over and over again, which we will use as an example over and over again to illustrate various topics. So that is why I wanted to be clear about what I'm calling each one of them. ABC are the 3 reflections, E, D, and F are the 3 rotations. Of course, doing nothing is also a rotation. It's a rotation to 0 degrees. So here we can see all the symmetry operations together. So D, 120 degrees to 40 degrees, and reflection in the 3 medians. Of course, E I'm not really showing because E essentially means do nothing. Now, one important point is that if you do 2 successive symmetry operations, then the result, of course, will be something which has to be a symmetry operation because the first one did not change the triangle. The second one didn't change the triangle. So, of course, doing one after the other will not change the triangle. Okay. So, any 2 successive symmetry operations on the triangle is a symmetry operation. So, just to illustrate that, let's start by doing A on an arbitrary point. So I hope it's visible. This is the arbitrary point P here in the triangle, and I'm doing A on it. What that means is I'm going to just reflect that point about the median marked A. So it goes here. And just to illustrate that you can do the same thing with the permutations symbols that I've written down, I've just written down the permutation symbol here. ABC equals to ACB. That's the permutation of vertices, which happens when you carry out small a. Now, if after you carried out small a, you carried out small b, which is reflection in this line. So if I reflect in this line, of course, this point is going to move somewhere here. So it's going to move here, and that's B acting on A, acting on P. And this is the permutation symbol for the permutation B. Of course, BAP that's exactly what I call BA acting on P. That's by definition of BA. BA is what you get when you do A first, then you do B. Now, just to point out, maybe you did not, perhaps some of you failed to notice this, but let me just point out that what I did here is I also switched this permutation symbol around a bit. Here it said ABC went to C, B, and A respectively. But in a permutation symbol, of course, all that matters is what goes where. It does not matter what order you wrote it in. So because the previous permutation, the one induced by A, ended in ACB, what I also did now is change the top line to read ACB, which is ABC went to CBA. That was the permutation. A, of course, is still going to C. C is now going to A, which is, of course, what happened here. And B goes to B. This one is the same permutation as this one. It has just been written slightly differently. And the reason for that is that the previous permutation that you carried out was on the original standard order ABC. It left it at ACB. Now this permutation is saying ACB will become CAB. So what happens when you do both of them together? Of course, A goes to C, B goes to A via C. So B became C first, then it goes to A. C goes to B. So the overall permutation that happens is ABC goes to CAB, which of course is this operation here, and which you can easily see is the same as the rotation through 4 pi by 3. So BA acting on P is the same as f of P for every point P, which of course means that I can replace the product BA, which is simply do A first, then you do B, by F. So BA equals F becomes a rule for this particular group. Similarly, you can check that after doing F, that is P, you started with P, you did F on that, it went here. Then you, if you rotated it by 2 pi by 3, which is D, you would come back to where you were. So D essentially undoes the action of F. So you do F on P, you go to a point, then you do D on that, you come back where you were. So that is exactly what you mean by the inverse. So inverse here simply means something which undoes the action of a particular group element. Now, it's obvious that if the original operation left the triangle invariant, undoing that will also leave the triangle invariant, right? So if the original operation is part of the symmetry group, symmetry set of symmetries, the inverse will also be part of the set of symmetries. Now this essentially tells us that if you collect all the symmetries together in a set and define multiplication of the symmetry operations by simply doing one after the other, you end up with an object which is called a group. So what exactly is a group? Again, this is something which is familiar to all of you, so I'm just repeating what most of you know already. A group is really nothing but an ordered pair. An ordered pair where G comma star, where G is a set and star is a binary operation. That is, it's a map from G cross G, which is all pairs of elements both belonging to G, to capital G. That's just a fancy way of saying star takes in two elements from the group G and returns to you an element of the group G. This star cannot be anything. There has to be some properties associated with it. And the properties are things like associativity. That is, it doesn't matter how you associate or put a bracket here. When you're doing G1, G2, G3, whether you do G2, G3 first and then apply G1 from the left, or whether you do G1, G2 first, then you apply G3 from the right, you must get the same result. So that's associativity. There has to be an identity in the group. That is, there has to be a special element called the identity, which in our example was just simply doing nothing, such that if you do E, or if you compose E with G or G with E, you are going to end up with G for all the elements in the group. And finally, every element in the group must have its own inverse. G star G inverse must be G inverse star G, and that result has to be equal to the identity. That is, you have to be able to undo the action of any group element by another element which is present in the group itself. Now, many of you may be wondering what happened to the most, the first group property which anybody lists, that's closure. I didn't list it so far, but this is for the sake of completeness. For all G1 and G2 in capital G, G1 star G2, the result of composing G1 with G2 must be in capital G. The reason why I did not list it for so long is that, frankly, if you are saying the star is a binary operation, then closure is automatically implied, right? When you say some star is a binary operation, it means that it takes two elements of G and gives you an element of G. So closure is implied the moment you say binary operation is something which you don't really need to list as a separate property. The reason why people like to list closure as a property is simply this, that closure, especially very often you're not very sure whether what the operation that you have is a binary operation at all. Or in particular, if you choose a subset of a set and ask, is there also a group in its own right, thus forming a subgroup, you have to now check whether if you take every pair of elements from within that subset and compose them together, do you get an element in that subset itself, or does it go outside? Now, closure, as I said, is implied by the term binary operation, but it's important to keep in mind that it has to be obeyed anyway. Now, associativity is actually one of the hardest properties to check. If you are just given a table for group products and asked to check whether this is really associative, you would have to actually take all possible triplets and just go through them one by one. A pretty long job. Okay. But one good thing is, in physics, almost always the kind of groups that we deal with are groups of transformations, things you do to a set. Okay? And associativity is trivial for transformations, where star just means successive application or successive transformations. Just think about this. What does G1 star, G2 star, G3 mean? In the context where G1, G2, G3 are transformations you apply on some object. It simply means you do G1 after you do G2 star G3. Right? Remember, when you write it in this way, A, B means you do B first, then you do A. So you do G1 first, G1 last, after doing G2, G3. But what is G2, G3? You do G2 after doing G3. So G1 star, G2 star, G3 simply means you do G3 first on something, then you do G2, then you do G1. And I will let you figure out that G1 star G2 star G3, written the other way, this one, means exactly the same thing. It means do G3 first, then do G2, then do G1. So as far as a set of transformations is concerned, which is what will be the usual scenario where we will use group theory, associativity will be almost trivial. And as you all know, we will usually drop the star when we write the product, simply because it is a lot of bother keeping on writing a star every time. And there are several results which follows directly from these basic properties. For example, you can easily show that there can be only one identity in the group. The proof is sort of trivial. You just assume that there are two, and you start with E1 star E2. Now, E1 star E2 has to be E2 because E1 is identity. It also has to be E1 because E2 is identity. So E1 star E2 is both equal to E1 and E2, and hence E1 and E2 must be the same. Similarly, you can show that that for a given element, the inverse has to be unique, and so on. And one very important thing is cancellation law holds. That is, because every element has an inverse, if AB equals AC, that will have to imply B equals C, because you can hit both of these by A inverse on the left. So A inverse and A will give you the identity. If you think about it, there's a lot of stuff that we are doing here. We are using the fact that A inverse exists. We are using the fact that multiplication is associative. So A inverse AB is the same as A inverse A acting on B, and A inverse A is the identity, and so on. But it's sort of easy, and it's something you get used to very quickly. You don't really have to go back and think of the basic defining properties all the time. And similarly, BA equal to CA, where A is on the right on both sides, can cancel out the A and write P equals C. But one very important thing, if AB equals CA, then unless you're dealing with a situation where the multiplication commutes, you cannot cancel A. You have to make sure that A is both on the left, on both sides it's on the left, or on both sides it's on the right. And the special case that I talked about right now, if for every G1 and G2, G1, G2 equals G2, G1, we call such a group abelian. And many important groups, both in physics and mathematics, are abelian groups. And finally, I started out by saying that a group is an ordered pair. It's a set and a product operation. However, almost universally, we will abuse language and we will say that the set G is a group G. So we will often talk about the group R under addition, where actually the group is R and addition both together. If you don't specify the composition rule or the rule for the binary operation, the group definition is incomplete. It's possible that the same group set may have multiple products defined on it that will give rise to different groups. Usually the operation, at least whenever the operation that you mean is obvious from the context, we will actually not talk of the operation. We'll just say the set G is the group G. That's a language which everybody uses. It's really not quite right, but people do this, and usually it confuses nobody. Okay, so let's talk of some examples. These are again examples which you all know. The real numbers, all real numbers under addition, they form a group. It's very easy to check the properties. If you add two real numbers, you get a real number. It's of course true that A plus B plus C is A plus B plus C. Associativity works. And there's a very easy way to check, understand that using ordinary language. In ordinary language, we often ask people to add 2, 4, and 5, right? We're not saying add 2 to the sum of 4 and 5. We just say add 2, 4, 5. We never say subtract 2, 4, 5. That would be ambiguous. Or divide 2, 4, 5. But we do say add 2, 4, 5. We say multiply 2, 4, 5. And the reason why we can say that, and it makes sense, is that both the two operations, addition and multiplication, are associative. So adding 2, 4, 5 makes perfect sense. You don't have to tell your audience where the bracket is. When you say multiply 2, 4, 5, whether it's 2 times 4 times 5 or 2 times 4 times 5, the result is the same. The result is not the same for division or subtraction. That's why you never say subtract 2, 4, 5 or divide 2, 4, 5. Okay. So associativity is obvious. Identity is, of course, nothing but the number 0. And the inverse here is just the negative of a number. So when you add it to that number, it gives you the identity. Well, R plus is a group because of this. Instead of R, if you use a set of all integers with plus, you would again get a group. Again, very simple to prove. In fact, if you just took positive integers, you would not get a group, because then you will not get negatives or inverses. Well, just to quickly continue with a few more examples. Again, very familiar example. So all real numbers under multiplication, this is not a group. This one is. But if you took all real numbers under multiplication, you would not get a group, for the simple reason that the number 0 will not have an inverse. But if you take the set R set minus singleton set 0, which means take the real line, drop 0 from it, all non-zero real numbers under multiplication, they do form a group. All non-zero integers under multiplication, however, do not form a group, because say, for example, the number 2 does not have a multiplicative inverse in that set. Well, some more non-trivial examples which are very often used in physics: GL and R, the set of all invertible or non-singular n by n real-valued matrices. GL and C, the set of all invertible n by n complex-valued matrices. SL and R as a subset of GL and R. Notice here, the GL and R really is the name of the set, but we call it the group GL and R because the group operation here, multiplication of matrices, is sort of taken to be obvious. SL and R is a subset of GL and R, is a set of all invertible n by n real-valued matrices with determinant 1. So it's not all invertible n by n real matrices, just those whose determinant is 1. The S here stands for special, where G is general in general linear and R. S is special linear. So special here simply means unimodular, or determinant is 1. Now that's a subset which is also a group in its own right. You can easily check that if you multiply 2 matrices with determinant 1, you end up with a matrix with determinant 1, and the other properties can also be easily checked. Similarly, you have SL and C. ON, set of orthogonal n by n real-valued matrices. SON, orthogonal n by n real-valued matrices M with determinant 1. SON will be very important for us, in particular SO3, the group of rotations, in a later lecture. Set of all symmetry operations of a geometric object, they form a group. That was basically what I started with. Of course, I did not start with an arbitrary object, but with an equilateral triangle. But it should be pretty easy to convince yourself that you started with an arbitrary object and just asked what are the operations which keep the object the same, and said that, okay, I can compose 2 such operations just by doing one after the other. They will definitely form a group. Another very important group, which will be discussed in some detail by other speakers, I guess, from the schedule that I see, is a set Sn of all permutations of n objects. So this is in fact such an important group that it has a special name. It's called the symmetric group of n objects. This is, in a sense, understanding the symmetric group essentially tells you how to understand every group, at least every finite group. So these are some examples that I have to talk about. Now, what I will do is I will just take a small break and ask whether there are any questions.
Hello.
Yeah.
Sir, are we allowed to unmute and ask questions?
Yeah, preferably, but if everybody does that, that might slow down. But okay, this is a nice time. You could just, preferably, I will just wait after a while and then ask for questions. Okay, that would be better, because otherwise it will slow down the thing a lot. So now is a good time.
I would have a question.
Yeah, please
so
go ahead. Go ahead.
Can I ask you now?
Yeah, of course. Go ahead.
So do singular matrices fall in this category? Would they also form a group?
Well, that depends on, first of all, when you say whether something forms a group or not, you have to be careful about what is the group operation that you're talking about. You take 2 singular matrices and multiply together, of course, they will be singular. The result will be singular, right?
Right.
After all,
right.
that much closure is given.
Right.
Okay.
Right.
Associativity will also follow because all matrices obey associativity. Yeah. Well, identity, will that follow?
Yeah, inverse would be a problem.
Well, even before that, identity will be a problem. To get to inverse, look, what is the inverse? Inverse is what gives you the identity.
Right.
Okay, you're right, that inverse will be a problem. After all, singular means it does not have an inverse in the standard multiplication sense of the word.
Right.
Right?
Yeah.
But identity, of course, is not a singular matrix. So your set, remember, it's a set you're talking about. Just saying that there's an identity somewhere will not do. That identity has to be in your set. If it's not in your set, then you don't have the identity, then you're not there.
Okay.
So, for example, if you just said take all matrices with determinant 2, they will not form a group. Well, there are several ways of seeing that. Even closure will not be the case here, right? If you multiply 2 matrices with determinant 2, you get a matrix with determinant 4. Okay, but if you just say take all matrices with even determinant, then the problem will be It'll again get stuck at the identity first, because identity has remained 1, which is not even.
Right.
Okay. So
Okay.
are there any other questions at this stage?
Thank you, sir.
Yeah, thanks. Thanks for the question. That's actually important. Are there any other questions at this stage? If not, I can move on to the next topic. I'm assuming from the silence that there are not. Am I going too slow? Or that is, am I saying things which everybody knows, so I can just skip them?
So this is fine, sir.
Yeah, but that comes at a cost that I may have to skip something at the end. But anyway, let's see. Okay, let's go back. The set Sn of all permutations, that's a very important group. And we will talk about that in some detail. In fact, other speakers will talk about that in more detail. But let me just give you some small details about this. In fact, the details will be scattered throughout the different lectures that I will give. But right now, let me just describe this to you, because some of you may not be familiar with the notation. Instead of all permutations of n objects, you start with n objects. We started with 3 vertices of a triangle, for example, a while ago. If you have n objects and you permute them, they form a group. And when you say objects, usually you just start by saying the numbers 1, 2, 3, 4, 5, 6 up to n. You don't have to. You can start with any set of n objects. But just using 1 to n makes the notation easy to handle. So basically, a permutation, a specific permutation pi, essentially is a onto map, 1-to-1 onto map from 1, 2, n to the set 1, 2, n. Because it's 1-to-1 and onto, basically all the elements are to be rearranged. You cannot drop, say, as a result of doing pi 1, pi 2, pi 3, pi n, it's not possible to drop out 4. 4 will be there at some pi of something. Similarly, you cannot have 2 different elements, 1 and 3, for example, give you the same result. There's a 1-to-1 onto map. It's just a rearrangement of 1, 2, 3, n in that sense. So this is the notation that we often use. You have already seen the notation a while ago when we talked about the triangle. In the top row, you just put the original elements in some order. In the bottom row, you write down what happens to them when you apply the permutation. So any permutation can be denoted this way. So pi 1 is what pi maps 1 into. What pi 2 is, of course, what my pi maps 2 into, and so on. Now, what is very important, and it's going to come back to be very important later also, a permutation can be denoted by a cycle structure. Now, what does that mean? Let me just illustrate with an example. Let's say this is a particular permutation that I'm talking about here. Notice that what this says is 1 maps to 7, 2 maps to 2, 3 maps to 5, and so on. Of course, you should realize that you have numbers 1, 2, 3, 4 up to 7 on the top row. You have the same numbers in the bottom row. They have just been rearranged. Okay. Now, when I say cycle structure, what I do is, well, I start with any one of the elements. Let's say I start with 1. I ask where does it go? It goes to 7, right? Then I look at what happens to 7. Where does 7 go? 7 goes to 3. Then I look at 3. Where does 3 go? 3 goes to 5. Then where does 5 go? 5 goes to 1. So I've got a cycle. 1, 7, 3, 5, 1. Right? That's one cycle. That doesn't tell me everything about the permutation, but it tells me that this is what happens to 1, 7, 3, 5, and 1. But after I've exhausted the cycle, I can then go on to another element which is not in that cycle. Let's say 2. This just says 2 goes to 2. So that's the end of it. Doesn't go anywhere. I've already seen what 3 happens to 3. So let's now go to 4. Where does 4 go? 4 goes to 6. 6 goes to 4. So that's another cycle. And that takes care of all the 7 elements. So when I denote this as a cycle, it looks like this. I don't write 1, 7, 3, 5, 1 because by default it's supposed to come back to 1. That's come back to where it started. That's part of the notation. So here this particular permutation will be denoted 1, 7, 3, 5. That's what happens to. It says clearly that 1 goes to 7, 7 goes to 3, 3 goes to 5, and 5 goes back to 1. That's the convention. Then you have a cycle which is singleton element 2. One cycle, 2 goes nowhere. In fact, very often in the notation we will just drop the 2. We will not even write 2 because it goes nowhere. So if you just don't write it, it means it doesn't move. And 4 goes to 6, 6 goes to 4. That's the cycle. Okay. So this is another way of writing down a permutation. As you will see later, this particular way of writing permutations will be pretty important in understanding the structure of the permutation group. So this particular permutation has one cycle, which is one cycle is simply one element moving in a cycle, which means it doesn't go anywhere. 1, 2 cycle and 1, 4 cycle. Okay. Right? So the 1, 1 cycle is this one, 1, 2 cycle and 1, 4 cycle. Now the cycle structure, how many cycles of what size does a permutation has, that actually becomes very, very important in deciding its properties, especially its properties, those properties of it which we are going to be very interested in. That will be clear, I hope, as the thing progresses. So now, okay, are there any questions about this? Specifically how you write cycles and how you multiply permutations. I've given you an example of how you multiply permutations, right, before. You all followed that, right? Essentially, you just figure out what happens to start with 1. After the first permutation goes somewhere. You have a second permutation after that. You just ask what happened to the result of 1 on the second permutation. And that is where 1 goes to ultimately. So you just write that down properly. There's a standard way of handling this so that you can do it fast. That's by rearranging the top row and so on. I hope there are no questions about that. Or if there are, please ask.
Sir, can I ask a question here?
Yeah, go ahead.
So actually, the cycle structure is just showing. It's good. The red side we can relocate where or what. How to relocate the placing of the elements?
What do you mean by the placing of the elements? You mean that originally it was 1, 2, 3, 4, 5, 6, 7?
Yes. So how to locate that with looking to the right?
Well, that is that the whole point is that's unimportant, right? The permutation essentially says, when you say look, a permutation is a map, right? What is a map? What is a map really? A map is basically a rule which associates elements in a domain to elements in a codomain. Okay, and domain and codomain are both sets. The order does not matter. So if I think this is an important point which let's just see whether I can illustrate this a bit. Say a permutation like this, 1, 2, 3, 4. I'm just writing any permutation that comes to my mind. A permutation of 4 objects.
Yes, sir.
Another permutation 2, 3, 4, 1. 2, 4, 1, 3. These are not 2 different permutations. They are 2 different ways of writing exactly the same permutation, right? Because here also 2 goes to 2. Here 2 goes to 2. 3 goes to 4, 3 goes to 4, 4 goes to 1, and 1 goes to 3 in both cases, right?
Yes, sir.
So these 2 permutations are identical. And if you look at the cycle structure, I will write 1. If I started with this, I will write 1, 3, 4, and maybe I will not even write the 2, or I could write the 2 if I wanted. Okay, that's the way you would have this. Here I would write 2,
Same.
3, 4, 1, but 3, 4, 1 is the same as 1, 3, 4.
Yes.
Right? It has exactly the same information.
Yes.
This is actually going to be very important later on when you try to count how many cycles you have or how many different permutations you have. I will perhaps not deal with this too much in my lectures, but I'm pretty sure there will be a lecture on the symmetric group and young tableaus and stuff like that, and there you will see this counting becoming very important. This notion of counting, the 3, 4, 1 is the same as 1, 3, 4, and so on.
Yes, sir.
So many of you must be familiar with permutations, combinations, and more importantly with various combinatoric tricks. And there, it would be easy to sort of understand how different things go. That is how these notions become very, very important. permutations are really different, which are not. Cycles actually don't care about what the order on top is, but that's important. That's actually useful because, say, as I said a while ago, suppose I had this particular permutation, and after I did this permutation, I also did this permutation 1, 2, 3, 4, 2, 1, 4, 3. One way to figure out what will happen there, of course, you can figure out what happens by just by saying 1 goes to 3 and finding out that here 3 goes to 4, so 1 will ultimately go to 4. But there's a quick way of doing this, which is this. You rearrange the top line here to exactly match 3, 2, 4, 1. And remember now what you're writing down is exactly this permutation, no other permutation. You're writing this one down as 3, 2, 4, 1 will become 4. 3 goes to 4. 2 goes to 1. So 2 goes to 1. 4 goes to 3. And 1 goes to 2. So when you combine these two together, you just forget about the line in the middle. It becomes 1, 2, 3, 4 goes to 4, 1, 3, 2. This is a sort of relatively quick way of combining complicated permutations together. But it all depends on the fact that it does not really matter what the order of the top row is. As long as you keep track of what is going where, the permutation is the same. Okay, any further questions?
Yeah, I didn't get this last part. What? Can you please repeat this? What was that?
Which last part? I said that if I, for example, here and here, you have two different ways of writing the same permutation. 1, 2, 3, 4 goes to 3, 2, 4, 1 here. And 2, 3, 4, 1 goes to 2, 4, 1, 3. But then doesn't matter what the top row looks like. What this looks like is unimportant. As long as you have the same information as to what goes where, they're the same permutation. So the cycle structure does not keep track of what order you wrote the thing in, but doesn't matter, because that's not important in deciding what a permutation is. And the last line, you don't have a question about this, I hope. How you combine two permutations?
Yeah, this combining the permutations. I didn't get.
Okay, all I did was I wanted to combine this permutation, that is, let's call this pi and this sigma, and I wanted to find out what is sigma pi. That is, what happens when you do pi first and then you do sigma. Okay?
Okay.
So I could, of course, do it this way. I could say, okay, let's start with pi. Pi acts on 1, takes it to 3, and then sigma takes it to 4. So sigma composite pi will take 1 first to 3 because that's where pi takes it, then to 4. So 1 goes to 4. That I could do. I could keep on doing it for all the elements. Okay. The quick way of doing it would be I just write down this permutation pi 1, 2, 3, 4 goes to 3, 2, 4, 1. Write down the permutation sigma just below it here, just for convenience. And there, what I do is reorder the top line. Instead of writing 1, 2, 3, 4, I reorder the top line of sigma just to what the bottom line here is 3, 2, 4. I write that as 3, 2, 4, 1. But note that this is really, this was of course pi, the same as this one. This here is the same as sigma. 3, 2, 4, 1, 4, 1 through 3, 2 is exactly the same as what I wrote here. 3 goes to 4, 2 goes to 1, 4 goes to 3, 1 goes to 2. So this is actually sigma just written in a different way. But once I've written these two in such a way that the last line of lower line of pi is the same as the top line of sigma, sigma pi simply means you drop this middle here. 1, 2, 3, 4 goes to 4, 1, 3. So that just takes care of applying pi first, then applying sigma. That's it. Okay? Any further questions?
Sir, the last part, what you said, is it always necessary to go from 1 to 3, from 3 to 4, like from right to left? I can also define something left to right also.
That's just a convention that you have to follow. One convention you have to follow. When you say sigma pi, do you mean pi first then sigma, or sigma first then pi? And okay, this is an important point because depending on which book you read, especially depending on whether you read an abstract mathematics book, you may find a different convention. Phases usually always
exactly. So in the Harnstein book, it is given the opposite.
Yeah, it would be, because in abstract mathematics situation, things are very often different because they are focusing more on the operations than on what happens to objects, right? Phases very often think of a permutation as permutation acting on something. right? So we write things this way. To us, it's natural to say sigma pi is pi acting first, then sigma acting. Okay? Or when you say it's a function f, decomposite f, that's what mathematicians also do. When gf acts on x, we define that as g acting on fx, right? F gets to act first, then g gets to act. That's basically because of the way we wrote the thing down in the first place. Okay? This is a convention. You have to, when you read different books, you have to be careful about which convention you're following. Especially an abstract mathematics book might very well have a different convention from ours. Even different physics books have different conventions, unfortunately. Okay? So that's something which unfortunately cannot be done much about. You have to live with it. Okay, let's move on. And the next part is really very trivial and simple, but we still need to go through it because we are doing the basic stuff right now. We are trying to form what is called the group multiplication table. Okay. So what is the group multiplication table? It's just a table which tells you what the group products are. So there's a table where the rows are labeled by the group elements. In this case, I'm back to the set of symmetries of a triangle, E, A, B, C, D, F. And you have E, A, B, C, D, F labeling the columns as well. Usually by convention, you use the same order, though not always, as you will see later. Okay. So what you really do is you want to form a table where this element is E star E, this element is E star A. That is, pick any element here, say take this element will be B times B. Or let's say this element. C first, since it's to the left, not C first. C is actually, when you remember, when we are doing operations, when I write C star D, I mean D to do D first, then you do C. Okay. That's again a convention. That's the one we are going to follow throughout. So C star D is going to sit here. So what we do is, what we want to do now is completely form this table. So let's see how we can do that. One part, of course, is sort of straightforward. These two lines, this first column and the first row, they write themselves, right? The first column is E, A, B, C, D, F, right? Because it's E is the identity, so this E is the identity. So this is E star E, A star E, B star E, and so on. This is just the same as whatever this column is. Similarly, this row is exactly the same as whatever is on the top, simply because this E is what is called the left identity as well. So when you hit an element with E on the left, you again get that element back. So these two, the very first row and the very first column is sort of trivial for every group. There's nothing much to do here. The work that you have to do is for the rest of it. Okay? So this is a very simple case. So I'm pretty sure many of you will be able to do it entirely on your own without any other help. But I still want to illustrate one method which can be used, and which with some modifications is used in more complicated groups as well. The basic idea is this. You first start by looking at the action of these group elements on an arbitrary point. Let's say I've picked a point P here on inside the triangle, and I've labeled this point by EP. Why? Because it's what happens when you do identity, that is, do nothing on the point P. Okay. If you do A on the point P, you go here. A is this like reflection in this line. Yeah, any questions? If you do A on the point P, you go here. Okay. If you do B on the point P, which is reflected in this line, you go here. If you do C on the point P, that is, you reflect along this line, you go here. You rotate through 120 degrees, you will go here. And if you rotate to 240 degrees, you go here. One nice thing about this is you can easily see that the medians divide the triangle into 6 sort of pieces. And EP, AP, FP, BP, DP, CP all sit in different pieces. So it's pretty easy to figure out which is which. Okay. And now, just to save on the notation a bit, I will just drop the P from the notation. I will just label each of these points by the group elements. So I will say this is the point E, this is the point A, this is the point F, and so on. What I really mean when I say this is the point F, I really mean this is what happens to the point P when I apply F on it. Okay. So now let's say I want to now create this, complete this column of the table. This element is already known. E star A is A, nothing much about it. We now need to form the other elements. So what is that? I do A first, that is I have moved E, which is the original point, to A. Then I will do A again, which is I will reflect in this line again. So what will happen when I do that? Of course, I will go back here. So A star A will be E. Well, B star A, that is do A first, then you do B. So on A, do B. You get here, so B star A is F. After that, you do C, which means you reflect in this line. Reflect along this line, this point A. A, remember, is what happens when you apply A first. So C star A, you apply A first, you go to this red point here, then you go to this point D. So C star A is D. Similarly, you can easily complete the entire line as well. Well, you can again start with another column, start with doing B first, that's a red point, then you successively apply E, which is of course the first line in itself, then A, C, D, F, A, B, C, D, F on that. If you do that, there's something which I will urge all of you to draw and do yourself, because it's a pretty nice exercise. It gets boring after a while seeing somebody else do it. It's actually more interesting if you do it yourself. Okay, but this way you can complete the entire table. And this way you have got a full multiplication table for this particular group. Now, one thing that you should be able to notice here, now that we have the full table, this row of course is same as this row. No other row is exactly the same. All other rows are different, right? The second row is not exactly the same as the first row and so on. But you have to realize one thing. The second row is actually a rearrangement of the first row. Every element in the first row is somewhere here. So is the third row, so is the fourth row, so is the fifth row, so is the sixth row. Every row is a rearrangement of the top row or of this row. Every column, if you look at that, you get exactly the same thing. Every column is a rearrangement of these columns. So none of the elements, every row and every column of the multiplication table essentially is a permutation of the group elements. Every group element occurs in some order or the other. Okay. And what is important, of course, here, this sort of looks trivial, but what we are really saying here is this. If you pick, say, this particular row, which is labeled by B, which means you multiply every one of the group elements by B on the left. So B star E, B star A, B star B, and so on. Of course, you are taking 6 group elements here, you are multiplying them by B on the left, you are going to get 6 elements. No biggie about that. What is important is all the 6 elements have to be different, and that's because there's a group cancellation law. B star G1 cannot be equal to B star G2 unless G1 is equal to G2. So all the 6 elements are different, which means this has to be a rearrangement of the top row. And that's the formal proof, if you want it. And so for rows and columns, the same kind of argument works. It's basically the existence of the inverse, which ensures that the rows and columns are just rearrangements. So how many ways can you rearrange the 6 group elements here? Of course, there are 6 factorial different ways of rearranging, out of which you have only 6 of them in this group. Okay. So the group here has 6 elements. We took the set of all permutations of 6 elements. That's the group S6, which has 6 factorial or 720 different elements. This particular group that you are seeing here is a subgroup of that. All the elements are some permutations of the other. And this is a very special case of a more general result. Every finite group with n elements is a subgroup or is isomorphic to a subgroup. The name isomorphic I'm going to explain soon, but just understand that they are essentially the same group as far as group is concerned. So you have Sn, which is the symmetric group of n elements, which is why Sn is so important. Every finite group essentially is, as a group, almost the same as some subgroup of Sn or the other. So this theorem is very important for mathematics. It's not so important for us because for most cases Sn is way too big. However, it just goes to show that because for example here you have only 6 element group and the S6 would be 720 elements, right? By the way, this particular group happens to be isomorphic to a permutation group. You have already seen that, right? They take the 3 vertices of the triangle. You have 6 permutations of 3 vertices, and there are 6 elements here. And in fact, what I showed at the very beginning, where each operation was essentially shown as a permutation, and when you do 2 operations one after the other, essentially you got that by doing this, got the same result by just doing a permutation after the other. That's essentially saying that you could replace the group elements by the permutations and you would not lose any information out. That would be a group S3. So in future, we will often refer to the group S3 when we actually mean the group of symmetries of an equilateral triangle. They are essentially the same group for all practical purposes. So we come to the next part now. This is subgroups and corsets. Well, definition first. A subset H of a group G is called a subgroup of G if it is a group in its own right, under the same multiplication rule as in G. This is very important. After all, different groups, different sets may have multiplication, may have group structure under different multiplication rules. But to be a subgroup, you have to be a subset, and the same multiplication rule has to be obeyed. And what must one check to ensure that something, a subgroup is really a subset is really a subgroup? You must check closure. You must check existence of identity. That is, you must check whether when you take 2 elements from the subset, you are going to get an element in the subset. You may go, after all, because the original set G forms a group, you take 2 elements from the group G, they will, and apply this composition rule, you will definitely get an element in the group G. So taking 2 elements from the subset will automatically give an element from the group. The composition will give you an element from the group. But it's necessary that the composition will give an element from the subset H, right? So you have to check that. That is one case where closure has to be checked. Similarly, you have to check whether the identity, which was definitely an element of the original group, is also in the subset. And the inverse of every element of the subset H has to be there in the group somewhere. But is it also in the subset? That's something you have to check. So there's a lot of things which has to be obeyed before a subset can be a subgroup. So if, well, there's one theorem which makes life very easy for us often. I'm going to state this theorem without proof, but I'm pretty sure most of you will be able to prove this theorem very easily. It says that if all the elements of a subset obey this, for every element of H1, H2 belonging to capital H, H1 times H2 inverse is in capital H, then H is a subgroup of G. Okay. So this is a theorem which is very useful. Okay, let me just illustrate how useful this is just by giving you an application here. Suppose I wanted to check that the orthogonal group ON is a set of all orthogonal n by n matrices, real matrices, is actually the orthogonal matrices, of course, all of you know, obeys this. OT is O inverse. So I want to check whether this is a subgroup of the GLNR. This is, of course, a subset of GLNR. All non-singular n by n matrices, orthogonal matrices, of course, have inverses. The transpose are their inverses, so they're definitely non-singular. So I just want to check whether orthogonal group really forms a subgroup or not. One way would be to check that whether when we multiply two orthogonal groups, orthogonal matrices, do I get an orthogonal matrix? Is the identity an orthogonal matrix? is the inverse of an orthogonal matrix and orthogonal matrix and so on. Or you can just do this. Take two elements O1 and O2 from On and check whether O1, O2 inverse is orthogonal. So how do you check that? You take its transpose, which is of course O2 inverse transpose, O1 transpose. O2 inverse, remember O2 being orthogonal, O2 inverse is O2 transpose, O2 that transpose of that is just O2. And O1 transpose is of course O1 inverse, which by the magic of inverses is the inverse of this, and so this does belong to On. So according to our theorem that we just stated a while ago, this theorem, what we have is On must be a subgroup. Okay. So any questions about this? I just have to keep on checking whether I'm still connected. Can anybody just confirm that you are still listening?
Yeah, it's completely fine.
Okay, you are. Okay, you are. Because unfortunately, when I'm in the presentation mode, I also lose any such feedback whether I'm connected or not. So I might be talking for a while without knowing what's going on. Anyway, let's quickly take a look at some subgroups which our standard example group has. This set of all symmetries of an equilateral triangle. It's very easy to see that if you take the elements E and A and just look at the part of the multiplication table which has just this, they form a subgroup, a two-element subgroup. E goes to E, E goes to E times A is A times A times E is A times A is E. Well, that's not the only two-element subgroup here. E times B, E and B form another two-element subgroup, which, if you really look at it, is exactly the same as this group, right? All that has happened is A is replacing B. So this is an example of an isomorphic group. In fact, you can easily show that there is only one two-element group really. If you just consider two-element groups, there's only one group. The two elements E and G must obey a multiplication table like this. There's no other possibility. In fact, you should be able to check by explicit construction. There is a good homework to do. That there's only one two-element group, only one three-element group. There are two different four-element groups as far as multiplication tables are concerned. There's only one five-element group and so on. Okay, not and so on. Things get more complicated as we go further, but those are sort of easy. Similarly, E and C form a two-element subgroup. EAB do not. If you take A and B, you can easily see this part that the moment you compose A and B, you're getting D, which is outside the set EAB. But EDF, that's the other subgroup this has. EDF forms this multiplication table, which I've just taken by picking out the corresponding rows and columns from the original table. And this actually is a group multiplication table. So you have a group here. So these are four subgroups. Well, actually, this particular group of ours, the six-element group of symmetries of an equilateral triangle, has six subgroups. Four of them I've shown here. Two others, well, one of them is a trivial subgroup which only the identity. Remember, a group at the very least has to have the identity in it. So the empty set is not a group, definitely. But you just take the identity. That's a subgroup. And the entire group, take all the six elements. That, of course, is a group in its own right. That's also a subgroup by the formal definition of a subgroup. So the formal definition of that's a subset by the formal definition of subset, so it's also a subgroup. So these are two trivial subgroups which every group has, just the identity and the entire group. Apart from those two trivial subgroups, this one has four others. Okay. Now, this is an interesting thing which, again, most of you know. Given a subgroup H of a group G, the left coset GH is defined as this. You just take every element small h from capital H, multiply it by the element G from the left. That's why it's called the left coset. G is sitting on the left. Similarly, we can define a right coset, capital HG, by taking every element from capital H, multiplying by G on the right. In general, HG and GH, they are both sets, but they are different sets in general. So just to illustrate, if you take the example, the one subgroup that we already talked about, EA, what are the cosets? Well, I can form the left cosets by multiplying EA, the E and A, by some group element from the left. So what I do is this. Here I am forming EH, which is of course trivially E times E times A is of course EA. The right coset, on the other hand, the multiplying element will come from here. The subgroup will be here. So this is the subgroup. Of course, this is trivial. EH and HE must always be the same as H. Well, what's not so trivial, but it's sort of obvious if you think about it. AH, that is A times E and A times A, will also have to be H. HA will also have to be H. But what about BH? This is BH, B times E, B times A, that's BF, an entirely different set. What about the right coset corresponding to B, HB? Well, take EA, look at this column, the column with says multiply by B on the right, you get BD. So notice that these two are different sets. So here left coset and right coset are different. And you can go through the entire thing, pretty straightforward. And you get, these are the left cosets and these are the corresponding right cosets. And notice, you can see something very special about the left cosets, right? EA is coming here, BF is coming twice, CD is coming twice. And what you notice is that each of the cosets have exactly as many elements as are there in the subgroup H. That's sort of obvious, right? Because you get the coset by multiplying every element of the subgroup by an element of the group. So you must get one element for every element in the subgroup. And there's no possibility of a match. It's not possible for A times E and A times A to both be the same. They have to be two different elements. So here, because you started with a two-element subgroup, you must have a two-element coset, right? But what's also interesting, what's really more interesting, is that all these cosets are either identical, this is the same as this one is the same as this one is the same as this, or disjoint. Notice BF and CD have no common elements, right? EA and BF have no common elements, okay? And this exactly works also for the right cosets. The left cosets and right cosets are not identical in these cases. But if you look at the different right cosets, just look at the right cosets, they're all either identical or disjoint, and they all have exactly two elements in this case. Okay, what about, let's try another example, another subgroup. Let's try EDF. So the left here again, this game is pretty straightforward. You should be able to play it yourself. So I'm just quickly going through the whole thing. These are the left cosets and these are the right cosets that you get. But now you notice something. Each coset has three elements exactly. And they're either disjoint or identical, as in the previous example. But in this one example, all the left cosets are identical to the right cosets as well, right? So as I said, left cosets and right cosets are not the same in general, but sometimes they will be the same. Okay, not always, but sometimes. Okay. Now, this what I've said right now is basically something which is which leads up to Lagrange's theorem. I'm quickly going through this because I'm pretty sure most of you can figure out what's going on here on your own. The end result of this is because all the cosets are either identical or disjoint, and every element of the group is somewhere or the other in a coset, the number of elements in the cosets must divide the number of elements in the group, which means the order of a subgroup must divide the order of the group. So this is a very important result as far as mathematical aspect of group theory is concerned. It is useful for phases, but not that useful. So I'm just skipping the details of the proof, but the proof is again very simple. It's just what I said a while ago, formalized. What is going to be perhaps more important for us, although it may not seem that important right now, is the concept of conjugacy classes.
Is the cosets form a group?
Do the cosets form a group? We'll come to that. Actually, the answer is no in general, yes in special cases.
Okay.
Okay, we'll soon see that. Well, first of all, when you say something forms a group, you have to understand how to multiply them in the first place, right? Cosets are sets, not elements. So to first define how to multiply cosets. We'll come to that. That will be part of our, that's part of the theory that we have in place for. The next important notion is that of conjugacy classes. I quickly skimmed over one statement about the cosets. That is, cosets partition the group. You all know what a partitioning of a set is, right? Every element of the set features in some partition or the other, and these partitions are disjoint. They don't overlap. So you're just breaking up the set into pieces. That's called a partitioning. What's special about cosets is not only do they partition a group, they partition the group in equal sizes. That is why the size of a coset must divide the size of the whole group. At least for finite groups, this is a very important result. Conjugacy classes give you a different way of partitioning, which is something like this. You first define two elements, the notion of two elements being conjugate. So when are two elements called conjugate? This is something which should be very familiar to people in physics. You have all done similarity transformations or similar matrices. The notion is very similar. An element G2 is said to be conjugate to an element G1 of a group if there exists somewhere in the group at least one element small g such that G2 is G, G1, G inverse. So if you can go from G1 to G2 by applying G on the left and G inverse on the right of G1, and if that gives you G2, then G2 is said to be conjugate to G1. Now it's very easy to check that this is what is called an equivalence relation. I hope everybody remembers what an equivalence relation is. If not, please ask. Is everybody sure what an equivalence relation is?
Yes, sir. Yes, sir. But I have another question. You have mentioned that we can partition the group for finite groups only in the previous slides.
Yeah. Look, I didn't say you can do it for finite groups only. I just said you can do it for finite groups. I did not mention anything about non-finite groups. You have to remember one thing. This is a habit which phases have, which is bad when you're using it in mathematical topics, of reading more into a statement than is being said. Okay. I said for finite groups this works. I did not say anything about infinite groups. I left it alone for a definite reason. This will work often for infinite groups, but sometimes it gives you trouble, and I'm not trying to avoid trouble right at this stage. Okay, so I did not make any statement about what happens for infinite groups. If I say something works for finite groups, it does not mean it does not work for infinite groups. If we have time, we will talk about infinite groups. In fact, we will talk about infinite groups a lot near the end of my 5 lectures. But we will see that there are some results which generalize easily from finite to infinite groups, some results which do not generalize that easily. Okay, and we will indicate some ways in which the generalization works. I don't have the time to go into all the details, so I will just skip those parts here. Okay, so let's come back to this. Everybody, okay, when I ask a question like this, that is everybody familiar with conjugates, with equivalence relations? Of course, that means that if you're not familiar, please speak up, because otherwise you will be...
No, please explain about equivalence classes.
That's important. I didn't say equivalence classes yet. I will talk about equivalence classes, but I didn't say that yet. Let's come to what an equivalence relation is. An equivalence relation essentially is basically something that generalizes this, the equality. So if you start with equality, which is a very simple and obvious notion to many of us, and pick some of its important properties, you get things like reflexivity. A relation is called an equivalence relation if this holds. For every A is related to A. Symmetric So, of course, there's some set S to which this belongs. If A is related to B, then B must be related to A and transitive. A is equal to B, A is related to B, B is related to C. Okay, I'm using this equality sign here, but this you can read this equality not as as A equal to A, but A is related to A by some equivalence relation. A is related to B and B is related to C implies A is related to C. That's called transitivity. In fact, equivalence relations are very, very important in physics in many places. For example, in thermodynamics, you have the notion of thermal equilibrium, right? Now, a system which is in equilibrium is obviously in thermal equilibrium with itself. So the reflexivity works. If A is in thermal equilibrium with B, what that means is you can take A and B and put a diathermal wall between them, nothing changes. Then B is, of course, in thermal equilibrium with A as well, so it's symmetric. And transitive, that's actually the so-called zeroth law of thermodynamics. If A is in thermal equilibrium with B and B is in thermal equilibrium with A, then A and C are in thermal equilibrium with each other. What that means is, in a sense, thermal equilibrium has the same properties as equality. Whenever there is an equivalence relation between these three properties hold, that means there is an equality hiding somewhere. And in zeroth law of thermodynamics, you do know what equality you are talking about. Something is equal when two body things are in thermal equilibrium, right? That's temperature. In fact, the fact that zeroth law of thermodynamics can define temperature for you essentially is because being in thermal equilibrium is an equivalence relation. The other two parts of the equivalence relation property, reflexivity and symmetry, is sort of obvious from the definition. The non-obvious part, the transitivity, is what actually is called the zeroth law of thermodynamics, that you can which essentially ensures that you can at all define a temperature. And what is important is that whenever you have an equivalence relation on a set, if you take all the elements which are equivalent to each other, and collect them together, they will always form disjoint partitions which break up the entire set. Why? Well, basically every element has to belong to some partition or the other because every element is equivalent to itself. So if nothing else, it will sit all alone in its own equivalence class. So if you collect all the equivalent elements together, that's called an equivalence class. So this is an equivalence class in which maybe this element, which is all alone, equivalent to itself, that's sitting there. Now notice that this equivalence class and this equivalence class are completely disjoint. Why are they disjoint? Because if there were an overlap, suppose these two overlapped somewhere and you had an element here, then that element would be equivalent to everything here because it belongs to the same equivalence class as this one. It will also be equivalent to everything here, but then transitivity would tell you that every element here would have to be equivalent to every element here, which means they would all together have to be in the same class, right? So either two classes are completely disjoint or they are exactly identical. They have to be the same class or there can be no overlap. Their intersection must be empty. So equivalence classes obey this. And if you take the union of all A's, that will give you the entire set. So that is what is also called a partitioning. any equivalence class gives rise to a partitioning. And by the way, if you are given a partition, suppose you have a set here and it has been broken up into pieces, which together form the entire set, but which are completely disjoint from each other, then you can easily define an equivalence relation. You can say two elements are equivalent if they belong to the same piece. You can say this one is equivalent to this one because they belong to the same piece. These two are equivalent because they belong to the same piece, and so on. And easily check that that's also an equivalence relation. So equivalence relations give partitions, partitions can give equivalence relations. By the way, I have run out of time now, and I'm only, say, 2/3 way through my first lecture. But so the problem will be, if I go at this pace, I will not be able to complete all that I wanted to complete, which may not be a very bad thing. So I want the opinion of the organizers about this. Is this pace too slow, or?
It's not my opinion exactly which really matters. The participants will tell. I personally feel that you could have gone a little bit faster, but it is always good to,
Yeah, so I am more of the opinion that if people are following, that's perhaps better. Whatever little I can teach in that time might be more helpful. Instead of trying to push a lot of things in.
That's why the pace of the audience is more important.
Yeah. So what does the audience feel? Anybody feels I'm going too slow? I feel I'm going too slow. Actually, that definitely is true.
No, sir, it is perfectly okay, I think.
It can be eased a bit.
That way I will not be able to cover everything, but that's fine, I think. Because at least I see that several speakers are also going to talk about the same topics in some detail, in some specialized applications. So even if I miss a few topics, it may not be that much of a disaster. Okay, but then will we break now and come back again at 4?
Yeah, I think we all break for tea. I cannot supply tea over this web platform.
Yeah, but we can all get our own tea, I guess.
So everyone have your own cup of tea, and then you come back at 4 o'clock. We will be here. So please be here. Just please, I would like to request you all to join in time. Please do not join in between. It is disturbing for the speaker as well as who is helping you to join. Okay. So please try to, if you are interested in listening to the lectures, please join in time. Okay. So we break for half an hour now. We'll be on again at 4 o'clock.
Okay. Thank you all for sitting through this.
Sir, I do have a question, but I will ask you after the tea.
You can ask me now, just before the break, if it's a short question.
Yeah, sir, it's a very short question. The last statement you gave that the partition gives you the equivalence relation, an equivalence relation gives you the partition. I don't understand that statement. Can you elaborate a little bit, sir?
No, all I said is there are two different statements here. If you have an equivalence relation, what I illustrated was if you have an equivalence relation already in place, you can actually get partitions out of that. Okay, that should have been sort of clear. That was this thing. That is, you just collect all the things which are equivalent in the same set, and every element must belong to some equivalence class or the other simply because of this. If nothing else, it's in its own equivalence class, and because of the fact that the two different equivalence classes must be disjoint or identical. So that's why it's a partition.
Yeah.
On the other hand, if you are given a partition, so nobody mentioned a relation, but they took a set, broke it up. Say you had 20 elements in the set, they broke it up, 10 elements in one piece, 5 others in another, 4 in another, 1 in another, and gave you those 4 pieces. That will also help you define an equivalence relation simply by saying 2 elements are equivalent if they belong to the same piece. That's it. You just say this pink dot, this green dot here and the green dot here are equivalent. Why? No other reason, because they are in the same piece. That's it. You should check that actually obeys all the properties of reflexivity, symmetry, and transitivity.
Got it, sir. Got it. Actually, I used.
So if you either have, by the way, just one more question. The equivalence classes that you get in thermodynamics what are the equivalence classes that you get in thermodynamics from the Zeroth law? Anybody tell me that?
Yes. Actually, what the things are these two I have
Sorry, you are breaking up, or maybe I'm breaking up. Don't hear you. If in a thermodynamic diagram you took all states with the same T, all states with the same T and collected them together, that would break
No,
the.
I mean, I was not. I mean, I was not looking for. Yeah, so I was seeing that. I mean, when I see the equivalence class and the partition, I.
Sorry, I again. Okay, let us break. Maybe after the break you will have a better connection.
Yeah.
Because I can't hear what you are saying except for bits and pieces.
I will be on only. You can write it in the chat box, and so that he can read it.
If we wrote it in the chat
Correct.
box, we can read it. But yeah, then.
I'll just close the meeting. So.
Okay. Fine. So let's leave now. We'll come back at 4.
Yeah, sure. We will see you at 4 o'clock.
Sir, am I audible to you? Yeah, maybe yeah, maybe the connect. Yeah, so yeah, so actually I